Hey everyone. In this lesson, we're going to keep working with Newton's second law. We're going to gain even more familiarity with the idea of net force and the information it gives you. So working with it as a starting point, right? And how it helps you figure things out. Like if you're told that it's constant velocity, then you know the net force is zero, or if you're told the specific acceleration, then you might be able to calculate what the net force is. And it can allow you to figure out values of other forces. So we're looking at cases where there's more than one force, a little bit more here. These ones are all just linear, so no scale diagrams or vector work needed, but just keep in mind that that might be a possibility, of course, in some questions. So here we go. So if we are given forces and mass, so in this question, we've got the 4-kilogram object, we've got an applied force of 10 newtons, and it's experiencing a 4 Newton friction force while sliding in the direction of the 10 Newton force. So you're told everything you need to know about the situation. And so the questions I would ask to help guide you through this kind of thing, instead of just asking like, what's the acceleration on the object, I might ask you to draw a free body diagram, determine the horizontal net force, and then of course that makes answering part C nice and easy. Leads you towards it, right? So let's go through that work. We have a dot for the object, and then we should have an applied force of 10 newtons, probably forward on the page to the right, probably on the page here, presumably, and then a 4 Newton friction force the other way, right? So you're going to have opposing forces in a straight line, so no vector work needed. You could have a situation where applied forces are in different directions. So if this is viewing from above, friction is always going to be just opposing the motion, of course. But if you had more than one force, right, you could look at adding force 1 and force 2 and have a vector and so on, right? Just consider that possibility. But friction kind of complicates that, because friction always just be against the motion, right? So why we have kind of linear cases here only. So determine the net horizontal force. Well, the biggest thing you have to recognize is that net force is always just the sum of all the forces just added up, right? So think of it as whatever forces there are, right? Added up. You get whatever force, all added up, right? And so we've got the 10 Newton applied force, which is going to be there. And then we've got the friction force, like that. And then you think about the rest of the information. There just aren't any other forces. But basically, I like to show it like that, to show the idea that you just have to add up all the forces, whatever there is. Leave it as an open-ended continuation of just adding up whatever there is. Because I don't want someone to think like it's always just applied force plus friction force, because there could be other applied forces, so there could be something else going on, right? More than one type of friction force, for example, would be an easy example. So the 10 forward and the 4 newtons back, listing this, we looked at the idea of the negatives for direction systems, right? So if I make this be a 10 Newton forward and a 4 Newton back, you get positive 10 and a negative 4. And so, of course, it becomes 10 take away 4 is 6 newtons. Okay, so we know the net force is 6 newtons. Then we looked at very specifically recently that if you have the net force, then you can determine the acceleration, right? And so we have a net force of 6 and a mass of 4, and we can determine the acceleration. Nice and easy. Plug in the mass and plug in the net force and just divide both sides, and you've got your acceleration. Right? In a question like this, of course, we could have a bunch of uniform acceleration questions afterwards, like how far does it go, and what's its final velocity, and so on and so on, right? But that would just be review work, and I think there's one of those in the homework just to keep you in tune with the idea of those skills. It'd be a good review question for the test we have coming up, of course. And next question. So in this question here, the key, there's a huge hint, obviously, with the title here, but you're given constant motion, right? But just, read this as a question here where you've got a 2-kilogram object being pushed with an applied force of 30 newtons against friction, and it has constant motion. So determine the friction force, draw a free body diagram, determine the acceleration it would have. If the acceleration was at a different value, what would the applied force be in order to make that happen, or what must it be in order to make that happen? All these kind of questions, right? And so we're going to determine the friction force. you need to kind of notice that there is some hidden information here, right? So because it's constant motion, that means we have a net force of 0, right? So the solution looks like that, where we say, okay, wait, let's notice that, where we have a net force of 0. And so we have net force is all the forces added up, of course, and we know that the result is 0. So we've got an applied force of 30 newtons, and it's against an unknown friction force, right? So we just leave it as a variable. So of course we can just subtract 30 from both sides, end up with a friction force is negative 30. Okay, so the negative means against the motion, of course, right? Obviously we could do some velocity, other uniform acceleration questions afterwards, but just get rid of that so you're not confused by what that is. And then notice this one here, I'm asking you to draw the free body diagram afterwards. Could ask before, but it just wouldn't know the sizes, right? So I feel like it kind of makes more sense to ask this afterwards, because then you have the actual values, but there would have been intuition here as well if I had have asked for the first question. So if it was A equals, draw a free body diagram, that would require you to notice this constant motion, net force is 0 idea right in here. So basically you'd have your free body diagram and you'd be saying, okay, well, I know I have two forces. I have the applied force and I have the friction force. And so they must be the same, right? So just basically make them be about the same here, and knowledge you could have done, really, right? So we know they're the same. Or opposite directions, but FA and FF. So we certainly could do the free body diagram first, but I always kind of, as a student, remember thinking like, it'd be kind of nice to calculate those forces and then get asked that. So I'd find myself doing parts B and C and then going back and drawing the free body diagram afterwards. Anyways. Part C. So determine the acceleration the 2 kilogram object would have if the applied force was 35 newtons instead. So we have, we want acceleration, right? So we should be thinking, okay, F net equals, figure out what F net is, right? And so we can figure that out. So now we've got an applied force and a friction force adding up, right? Leaving it open for more forces, of course, right, as always. But yeah, we have our 35 plus our negative 30 still. So we have a 5 Newton net force. And so obviously then you're like, okay, well, I know the net force and I have the net force. I have the mass as well, I should say. And so you can get the acceleration. Okay, so now we're looking at it as if we push a little harder, we can make it accelerate at a predictable rate. And in part D, if the acceleration was a specific value, not the same as this one, notice it's pretty close, but what's the applied force that would make that happen, right? Well, the first question that you have to notice you need to do is determine the net force, then you can get the applied force, right? So sometimes parts A, B, C, or I and I or whatever are there to kind of help you along the way. Sometimes students think it makes the question look like it's longer or harder, but it's actually there to help you get there, right? Show you the kind of steps along the ways you need. So we have this mass and acceleration, and we know F net equals ma, and so we have the kind of have both in one here, right? We have the net forces, all the forces added up, and we have our mass times acceleration concept. So what applied force is needed now? We have that same friction force. What's that applied force that you'd need? So you have F net equals 4. So then you have 4 equals an applied force plus a known friction force. And you just add 30 to both sides, and so you should need to have an applied force of 34 newtons. All right. One more I'll run through with you. Again, of course, I'm hoping you're still thinking of the idea of pausing and trying yourself, of course, right? Especially with this one, since I've gone through it. So it'd be a good idea to pause here and look at it, try it. Then when I'm taking it up, you can say yes or no if you're good to go, right? So we have this 1,800 kilogram car flying down the road, constant velocity of 115 kilometers per hour, and so on. And I'm walking you through this a bit here, saying like determine the net force, draw the free body diagram, all these things, right? But you could just jump right to, um, what's the force needed to keep it going, or so on. So the big thing here, of course, notice that it says constant velocity, and we have this like constant velocity, F net equals 0 from that previous lesson, right? So we have the net force is 0, of course, which a lot of people have problems with that, right? Lately, actually, there's been a lot of people answering incorrect for the projectile motion situation where we have a ball going up and down. And the question is, what's the acceleration? What's the velocity and acceleration in each spot? So right now the velocity is up and the acceleration is still down. And then the velocity was up and the acceleration is down. Here the velocity is 0, but the acceleration is very much still down, and a lot of people have been saying 0 by accident, but the acceleration is that same negative number as it always was, right? So that's one of those like intuitive ones. It's hard. It comes back at you, and I've been giving a lot of feedback on assignment submissions there that no, it's at the top. It still has that down acceleration due to gravity, or else it would stay there, right? So a lot of people are saying it's like for a brief moment it has an acceleration of 0. The answer is no, it doesn't. This is another one of those ones where you're like, but it's a car and it's going down the road at a fast speed. It can't have a F net of 0, and I'd be like, it absolutely does have a net force of 0 because it has a constant velocity. Okay, you just have to recognize that there's an applied force and a friction force, of course, right? So you gotta just get that out of your pre-programmed experienced brain, that you need a force to keep going, which is not wrong. You do need a force to keep going. You just don't need a net force to keep going. Okay, so a free body diagram of things easy. You just have balanced forces. The applied force and the friction force have to be the same. Okay, so if the force of air resistance was 2,500 newtons, determine the force of the engine to keep up, and so on. Obviously, we know that the net force is 0. And we know that there's an air resistance force and an applied force. And so, you can just add 2,500 to both sides mathematically to show specifically, but we already determined here that they're just the opposite force. So you really could just use that analysis and say that the applied force has to be 2,500 newtons to balance the friction force. You just might need a little more wordy communication rather than mathematical solution communications for it. And part D, to pass, they want to accelerate at 2 meters per second squared. So that's the typical, where you're like, okay, I have an acceleration now in a mass. I can figure out what the net force needs to be, right? So air resistance is going to be the same until the velocity increases. So basically, at this instant, we can say we have that same air resistance. Obviously, the acceleration is going to allow us to calculate the net force. So here we go. We have the mass times the acceleration. So we need a net force of 3,600. And so we have some bigger applied force adding with the 2,500, right? In the opposite direction, of course. And so if you were doing the math, you'd be able to actually put numbers in there and draw the sizes relatively correct, right? That's not that you have to measure a scale diagram or anything, but you kind of want them to be reasonable at least, right? So we have a net force of 3,600. We have an applied force that we don't know, and we have the friction force of the minus 2,500 until it starts getting faster and faster. More and more air resistance, of course. We just add 2,500 to both sides, and we get our 6,100. So basically draw this arrow so that it's representing 6,100 in comparison to the 2,500. That's the idea of those. A lot of these are pretty quick and easy. Not as many parts to it as the examples I gave, but I kind of went through harder cases for you so that you can tackle anything later on. But these are nice simple ones, I think. If you follow along here, we do have one that is a vector version. So watch for that. Okay, this east and west. Oh no, we don't. Those are just linear. Never mind. I was thinking like north and west or something. So you don't have to worry about vectors there. So yeah, we're good to go, but just keep in mind vectors could be a possibility. Again, north and south opposing directions, so everything's linear here. All right. So we go. Thanks for watching, everybody.